So, welcome everyone. Thanks for being here. This is our second doctoral meeting on aerospace, on the PhD program on aerospace science and technology. Today we're going to be discussing about propulsion and the space environment. We have 7 presentations of 7 PhD students, namely Alberto Marin, Alberto Modesti, Enrique Bello, Jesus Perales, Marco Ricardo Inchingolo, sorry for the pronunciation, Pedro José Jiménez, and Tatiana Pegotin. They are doing different PhD theses on um, electric propulsion, both numerical and experimental, and they're going to be telling us what they have done so far in the first, second year of their PhD thesis. The goal of these doctoral meetings is to gather together, to get to know what the PhD students are doing, for you PhD students to share your progress with your supervisors, a qualified audience in the department faculty people, but also your peers, other PhD students, so that you can also get to know what others are doing, have discussions and foster collaborations and exchange of ideas, which is a very important part of our research. So now, having said that, I would like to thank you all for being here.
My thesis focuses on the numerical simulation of the propagation and absorption of electromagnetic waves in plasmas, and in particular the applications to a new generation of thrusters called electrode-less thrusters. So for those of you that don't work in electric propulsion, let me very briefly present these devices because they are relatively new, and this is a novel technology. So the principle of operation of these thrusters is based on the radio frequency coupling of the electromagnetic waves coming from an antenna that hit the plasma and ionize the neutral gas. And then we have the acceleration of the charged particles in a magnetic nozzle that is created with a set of solenoids or coils. Because they don't have any electrode or acceleration grid, there is no erosion of sensible parts. And these devices promise longer lifetimes, high throttability, also a higher thrust density than classical devices. And a hot topic nowadays in electric propulsion, the potential to use alternative propellants. Nevertheless, there are some challenges before entry into service because these devices are not generally flown. They are not the typical thruster that we find in most satellites. The main one is increasing the performance because nowadays the efficiencies are quite low. And for this, we have to understand much better the physics of the device. There are several mechanisms that we need to understand, and in particular, a plasma wave interaction is really important. Sorry. It's really important because it is the main way that we can energize the plasma in these thrusters. So the wave propagation problem in plasmas has been studied for many years in a lot of fields. And interest in electric propulsion has increased recently because of the coming of these new thrusters. It is a complex topic. And to illustrate this, even assuming the simplest model that we have, which is that of a cold plasma, neglecting any temperature of the charged particles, you can see in this diagram that we have a lot of propagation regimes depending on the plasma parameters, and the topology of the waves changes quite a lot if we vary, for example, the plasma density or the magnetic field. Also, I wanted to show you in this figure here to illustrate the complexity of the problem. Here I'm showing the electric field norm in a very simple case in which we have an out-of-plane current exaggerating the electromagnetic fields. And what we see is that we have an isotropy with respect to the magnetic field direction. So in vacuum, we would respect cylindrical symmetry with respect to this out-of-plane antenna, but you see that the plasma changes completely the propagation characteristics. And one last remark that I wanted to make is that when we change plasma parameters, for instance, in this figure, we are decreasing the magnetic field, we have changes between the propagation regions, and the topology of the propagation changes abruptly. And these critical transitions are very difficult to treat numerically. For instance, here we have the electron cyclotron resonance, and you can see that the electromagnetic field cannot propagate downstream. So this is something very problematic when you want to do numerical simulation of plasmas. And this is just for the simplest model that we have, the model of a cold plasma. If we want to couple this with the plasma transport, that is something we already did, the problem becomes nonlinear, it is even more difficult. And if we want to solve self-consistently the smaller time scales of the wave propagation and the dynamics of the fast electrons, we need a kinetic model retaining the temperature and kinetic effects. And this is very costly computationally, also very complex. So for my thesis, we have two main work packages or two main models. On the one hand, we have full wave 2D axisymmetric cold plasma codes. And I like to see these as engineering tools that will eventually be used by any group designer to optimize the thrusters and to design them. So what we do with these codes is to integrate the Maxwell's equations in the frequency domain. Here you can see the wave equation, and all the effects of the plasma are contained inside this dielectric tensor. Of course, this is still a cold plasma. And the codes that we have developed, the finite difference and finite element codes, are aimed directly at the design and optimization of the thrusters that we test in the lab and we develop in the group. And then we have a more fundamental science part of my thesis, in which we are developing an electromagnetic kinetic code that integrates the Blasat-Maxwell system. This is a nonlinear integral differential system of equations. As you can see here, is far more complex than the wave equation on the left. This retains all kinetic effects, but the problem with this is that we cannot have detailed geometric models of the thrusters because computationally it is impossible. So we need some simplified models of the thruster. We want to study the basic physical mechanisms underlying the power absorption in the plasma, and we also want to study the kinetic effects and whether the cold plasma is a good assumption for the full thruster simulations. So those are more or less the two parts of my thesis. We already have results on the cold plasma codes, and here we have some conference publications. So it is important to say that my thesis builds from two previous theses on this topic from the group, one by Bintian and the other by Álvaro Villar. I have a finite difference axisymmetric code. We have some improvements from the previous code created by Tian, like pre-processing, post-processing utilities, a new scheme, arbitrary azimuthal numbers in the arbitrary Fourier numbers in the azimuthal directions, and also larger domains to study the plume and other regions. We are also developing a 2D finite element code that will soon substitute the finite difference, the current finite difference code. Okay, another milestone of my thesis was the integration of the finite difference wave code with Hyphen, which my colleagues already explained, which is a multi-thruster simulation platform. This was important and was driven by the improvements in performance of the finite difference code, because this is really demanding. We are calling the power absorption from the wave code many times in a Hyphen simulation. We also presented some results in a past conference. And this allows us to study the full physics of the steady-state operation of the thruster and obtain all the profiles, like the plasma potential, the densities, and the currents. So just to give an example of the work I'm currently doing, here I have some results that we presented in the Space Propulsion Conference in March. So previously we were carrying out simulations in a small domain. Here you have the thruster and part of the plume. This is an axisymmetric simulation, so the axis of symmetry is located here. And what we did for the Space Propulsion Conference was to enlarge a lot the domain. So we were able to study the plume and part of the vacuum chamber. We also included some internal boundaries, modeling metallic parts like the coils and the backplate of the thruster. And we obtained some interesting results that were not previously published in the literature. And in fact, we are working on a journal article to present these results. So we see that, for example, we have a noticeable power absorption at the plume, and this was not reported before. And also the role of the electron cyclotron resonance in helicon thrusters was not, people didn't pay much attention to this phenomena because in principle it happens outside the thruster. But what we see is that the power cannot flux downstream the electron cyclotron resonance, and this is also an interesting result. This was the power absorption, and then we do other kind of analysis. For example, here I'm plotting the phase of one of the components of the electric field, and we can compare the wavelengths that we obtain and the propagation regimes that we are seeing with the classic cold plasma theory, and we obtained compatible results with what we expect from analytic results in the literature. Well, for the other part of my thesis, we are developing this Kinetic Code. So we are going to focus now on this in the coming months. This is a blast of code. It is not a particle in cell. So it's a bit, it's not so common in the literature. We are solving for the electron velocity distribution function. And we use a method that does backpropagation along the characteristic lines of the system. We want to have a 1D 3V model. So we are discretizing one dimension in space but 3 velocities. And this way we can study arbitrary wave polarizations. So for instance, a simplified model of our thruster would be a magnetic nozzle expansion with appropriate boundary conditions and a varying magnetic field. We will also have a collision model as a source term in the Boltzmann equation. The current state of this code is we have a prototype. We have tested electrostatic cases. So in this figure here, for example, you can see the two-stream instability, which is a typical kinetic example. The weighting module is ready, but we have to, and also the Poisson solver are ready, but we have to include the electromagnetic propagator that we have tested independently, but it is not coupled yet. We also have some basic parallelization. So for future work, in the cold plasma work package, we have to finish the finite element code and test it, and also integrate it with Hyphen, so everybody in the group can use it to study electrodeless thrusters. For a kinetic code, we have to integrate the electromagnetic propagator and perform a lot of tests. So this is in an early stage. We want to study simplified thruster models like the one I showed you in the last slide. And finally, we would like to explore other methods because this is a state-of-the-art topic. There is not much literature in electromagnetic kinetic codes. But there are some promising options like conservative schemes that we will like to study. And along the way, we are improving our high-performance computing knowledge and using modern tools like the Julia computing scientific computing language, which gives us high-level syntax but allows low-level operations, so we can have performances closer to Fortran and C. Yeah. And that's all for my part. So thank you very much. I work within Hypatia and Prometeo projects, by the way.